Welcome back, ladies and gentlemen. We're moving on to section 3.6, day 1. This is the chain rule. Alright, we're going to be finding derivatives of functions using what's called the chain rule, and here it is. Okay, basically if some function y can be thought of as a composition of two other functions, in my specific example, f of x and g of x, then the derivative of that function y is going to be the derivative of the first function f with the other function still inside of it times the derivative of the kind of inside function. Okay, now maybe that doesn't make a lot of sense, but hopefully a couple examples will get you there. Alright, so here's a composition of functions. I've got kind of a x squared sort of function, and then I've got a 3x minus 4 as kind of the inside function. Alright, so demonstrating what I mean relative to this. Alright, there's my function, so my y prime is, okay, again, I'm looking at this as an x squared, or a u squared, if you want to think of a different letter or something like that. So if I have something squared, that 2 comes out in front, and then I have that something that drops down to the first power. Okay, now the chain rule says that I have to do that, and then I have to multiply by the derivative of the inside function, in this case a 3x minus 4. So, following the chain rule now, I've got 2 times my 3x minus 4, and I'll just leave that alone for now, just to help stress what's going on, and then times the derivative. Okay, the derivative of 3x minus 4 is a nice simple 3. Alright, so a couple steps here just to play cleanup. I'll put the 2 and 3 together to make a 6, and then I'll distribute that into the 3x minus 4, so I get my derivative is 18x minus 24. Alright, so maybe that looked like a lot of magic wand waving, but if we imagine taking this and foiling it out, we should get 9x squared minus 24x plus 16. Okay, now let's use the good old regular power rule that, of course, we've been using for a little while now. 2 comes out, hits the 9, makes this an 18 with an x on it, and then the x goes down to a nothing, and we've got the 24 just hanging loose, which obviously is the same exact thing as we just came up with. Alright, so the chain rule did get us the same answer as the kind of regular way, but of course the chain rule becomes necessary because not everything is a polynomial you can just FOIL out to get to a more simplified version of it. For instance, maybe our function is a trig function of some sort that has a polynomial inside of it. Alright, so again, what the chain rule says to do is to take the derivative. Again, I'm looking at this as cosine of u, if you'd like. And so what I basically have now is the derivative of cosine is negative sine of that thing, whatever it is, in this case 8x minus 1, and then we have to multiply by the derivative with respect to x of whatever that inside thing was. So I've got a negative sine 8x minus 1, and now I'm going to have to multiply that by this guy's derivative, which is a nice clean simple 8. And again, that's a little bit messy, so I'll clean it up, bring the 8 out in front along with the negative sign that was already there. It gives me negative 8 sine of 8x minus 1. And there's your chain rule derivative. The chain rule also becomes very nice when you have something of this sort where you've got a radical sign with some messy thing inside of it. Admittedly, that's not that messy, but again, one thing that's nice to do is instead of this root being on the bottom, because I can think of a root as a power, is to rewrite this whole expression as 4 to the 3x minus 2 to the negative 1/2 power. So I can just use my power rule here. Although, because I have something a little bit messy in here, I am going to have to use the chain rule because the derivative of that is more complicated than a simple number 1. Alright, so here we go. We got y prime. Alright, again, the 4 is hanging loose out front, but the negative 1/2 jumps out front and hits it, getting us down to a negative 2. And then that thing, whatever it is on the inside, stays put, but my exponents drops down to a negative 3/2. But then again, I have to now multiply by the derivative of the 3x minus 2. Hopefully at this point I can just say the derivative there is 3. And then again, as per usual, I have a little bit of cleanup to do here. The 3 is going to hit the negative 2 and give me a negative 6, and it's one of those things where I started with a fraction-y sort of thing, so I'm going to end with a fraction thing, although I confess I'm not going to go to a root because I think that looks even messier. So 3x minus 2 to the 3/2, positive 3/2 now that we're down to the denominator power. And there's our derivative. I'd like to do one more of the kind of regular chain rule. This one's a little different for two reasons, and the obvious one is that I no longer have x and y, I've got r and theta. The other one, there's something that may be obvious to you, but maybe not obvious to you yet, so let's kind of get into it, and we'll see if you knew this in advance, or if it was a surprise when it happened. But, okay, again, here's one thing where I've got the root, and again, roots are kind of messy, so it's a good idea, I think in this case, to rewrite this thing as theta tangent theta all to the 1/2 power. Just makes taking the derivative easier. Okay, so I'm going to not use the r prime here, just to kind of stress something real quick. I'll use my d notation. So again, I'm going to use d, and since I'm using the primary letter r, my function is kind of an r, I'm use dr. And remember, on the bottom, I want to use d and then whatever variable is used in the function itself, and in this case, that'll be a theta. So I'm actually doing dr d theta here, not dy dx. Okay, just pay attention to the letters you use and use them appropriately there, if that's what's called for. Okay, that being said, I can go on with this thing now. The 1/2 jumps in front. Okay, and then this thing just kind of sits right where it is, tangent theta, and it drops down to the -1/2 power. But now I have to take the derivative with respect to theta of theta tangent theta. Okay, now here's what maybe you spotted right away, maybe not, but because this is a multiplication, I'm going to have to use the product rule. Okay, so don't let it throw you, it's just, a rule we've been using for a little while now, so just use it appropriately. Alright, so my dr d theta, okay, I've got my 1/2 times this thing, which I'll eventually clean up. Let's not worry about it quite yet. So -1/2. Okay, now big parenthesis here because I have to do my product rule. So again, first times the derivative of the second. Derivative of tangent is, of course, secant squared theta. Okay, now I've got plus the second times the derivative of the first. So now I got my tangent theta times a 1 because the derivative of theta, again, remember theta is just my variable. Just like x to the first is 1, theta to the first is just theta, or is just 1. So there you go. Alright, so now, like I said, we've got a little bit of cleanup to do. So dr d theta equals, okay, the -1/2 is going to take that down into the denominator. So I've got a 2 that's also down there. And now, again, I'm going to turn this back into a root because I don't have a root to a power other than 1, and really who cares about the 1 power. Alright, so there's kind of like my original. I'm dropping down to the denominator, and then my numerator is just a 1, and then this messy looking thing right here, theta secant squared theta plus tangent theta. So yes, it's messy, but that is the derivative. Alright, well, as it says there, it gets worse. Alright, so basically, it may not be obvious right now, but this function is actually kind of 3 functions all nested within each other. Alright, so first of all, I have a quantity square, so that's function number 1. Function number 2 is 2 minus some kind of a sign. Function 3 is it's a 5x instead of just a regular x. So it's kind of a triple composition, if you will. Alright, so here it goes. So I've got my y prime equals, okay, again, the first outsidemost function is my square. So the 2 comes in front as a coefficient, and then I've got my original function inside, 2 minus sine 5x. And then again, I need to multiply by the derivative with respect to x of the inside thing. In this case, that's 2 minus sine 5x. But again, notice that the 5x is its own function inside of the sine, so I'm going to have to chain rule again when I get to that point. And that's coming up right away. Okay, to save a little time later, I'm going to distribute this right here. So this becomes 4 minus 2 sine 5x. Okay, now the derivative of this guy, okay, conveniently 2 becomes a 0. Derivative of negative sine of 5x is going to be negative cosine of 5x. But again, since that was not something simple, I need to do its derivative as well. Okay, fortunately 5x is an easy derivative. So y prime equals 4 times negative 2 sine 5x times negative cosine 5x times the derivative right there is just a nice simple 5. Alrighty, so we do have kind of a yuck sort of situation here, and we're going to clean it up a little bit. But I'm going to bring this negative 5 cosine 5x out in front to maybe help show what's going on here. Negative 5 cosine 5x. and then we're eventually going to distribute that into the 4 minus 2 sine 5x. So all I really did here is rearrange things a little bit. So leading me to my final answer, as I distribute this, I get a negative 20 cosine 5x. Negative times a negative gives me a positive. 5 times 2 is 10, and then I've got a cosine 5x times the sine of 5x. And there is your triple composite function derivative. Alright, final example for this lesson is something that looks pretty simple right off the bat. Cotangent, I just want to find a derivative, but wait a minute, I'm finding a second derivative. Okay, well, for cotangent, well, that was from our trig lesson, so that's a pretty simple first derivative. Our first derivative is negative cosecant squared x. Alright, so easy enough. But as I start taking my second derivative, again, now I look at this thing, and again, it's kind of a nested sort of situation, because I've got my squared function with a cosecant function inside of it. So it is a chain rule situation. Alright, so here we go. Okay, I got my negative sign, which is easy enough to just leave out in front, but now my 2 comes in front, and I've got my cosecant x down to the first power now. But again, chain rule, I have to now take the derivative with respect to x of my cosecant, again the inside function. Okay, the negative doesn't apply because all I was looking for is the thing that was in the inside, and that's just the cosecant. Alright, moving on. Y double prime equals my negative 2 cosecant x times the derivative of cosecant is negative cosecant cotangent. Okay, so maybe this isn't as bad, but here it is. The two negatives cancel each other out. We got a nice 2. I got 2 cosecants multiplied together, so I've got cosecant squared x, and then the cotangent x just kind of hang on this right there. Alright, so basically, there it is. There's a second derivative, and just kind of pay attention. Sometimes you may not start with a chain function, but if you're going into multiple derivatives, sometimes one shows up. Anyway, there it is, and of course, any questions, I'll see you in class.